Okay, just doing random exercises. Ben Nicolay suggested some that I should do. So first one, 4.321, we're working with intervals and increase and decrease. Let's take a look. I got to find it. And I haven't prepared these at all. I'm just kind of looking at them. Okay, so number 21. So f of x is x squared ln of x over 2. Okay. Hopefully I'm picking the right ones. If not, just let me know and I'll do some more. But for these guys, you want to find the interval of increase, decrease. You need the derivative. It's not a bad idea to mention the domain in these. That'll help you when you draw your number line, that sort of thing. So in particular for natural logs, we need whatever goes inside of here to be greater than 0. Okay, so in particular, I need the x over 2 to be greater than 0. And if you multiply both sides by 2, you see that the domain needs to be all values x greater than 0. So when you go to your number line, you need not consider anything out of that interval. Okay? Okay, so now we need to get the derivative and all that good stuff. So f prime of x, we need a product rule. So leave the x squared alone. And then take the derivative of this. So it's 1 all over the guts times the derivative of the guts, which is 1/2. And then plus, let me quarantine this guy, plus the derivative now of x squared, which is 2x times the ln of x over 2. Okay. All right, so clean it up. So 1 over x over 2 is the same as 2 over x. So I rewrite that. And then these 2's will divide out. And then x squared over x is just x. And then plus 2x ln of x over 2. Okay, we need to set that equal to 0 and solve. So you can factor out 1x. And you'd have 1 plus 2 ln of x over 2. So one of the critical numbers is at 0. And then the other critical number we can get from this expression, setting it equal to 0, 2 ln of x over 2 equals 0. Move the 1 over. So 2 ln of x over 2 equals, what is it, -1. Ln of x over 2 equals -1/2. And then exponentiate both sides, and you get x over 2 equals e to the -1/2. Multiply both sides by 2, and we have another critical number. Okay, so then I could go over my number line for the first derivative. I'm starting at 0, so this critical number I don't have to worry about, but I do have to worry about this guy, right? So I got 2e to the -1/2, and I should make this like an open sort of parentheses, not a bracket, but hopefully you kind of get the idea. So you need your test value, you need your sign, you need your conclusion. If I were giving a take-home test, that's what I would expect to see. 2 times e to the negative, so there's some worry about what the heck that number is. I bet it's greater than 0.5 though, right? So you could pick as a test value probably something like 0.5, and then plug it into this formula here if you wish, wherever your derivative is, right here. So maybe you put something in there that works a little easier in the natural log. So if you put, I don't know, 2e to the negative, something that's going to be, smaller than that. I don't know. I'd rather not think about it at this point, right? Okay, so this number right here is 2 all over square root of e, right? E to the 1/2. I want something smaller than that number to plug into here. That's not going to cause me to have to go to my calculator and type in 3 million things. Okay, so if you pick something like 2 all over e, Now I want to make this number bigger than this number, e to the 1/2, right? So instead of taking the square root, if you just leave it as e, it'll have a bigger denominator, therefore be smaller than this thing. Okay, so if you put 2 over e into here, you'll have 2 all over, 2 all over e times 1 over 2, so it ended up being 1 over e. The ln of 1 over e is the same as the ln of e to the negative 1, and then that'll just be negative 1. So it'll be 1 plus negative 2, which will be negative, and you're plugging in something positive on the outside, 2 over e, and for x, right? So you get a positive times a negative, and at the end of the day, if you use it should be a negative, so it's going down here. Okay. And then on this side of it, we probably want to put in something such that this is smaller, right? So say e to the 1/3. Okay. So if you decrease the denominator, you make the fraction bigger. So I'll use that as my test value, 2 all over e to the 1/3. And then if you plug that into here, on the outside, you have a positive thing. And here it'll be a 2 all over e to the 1/3 divided by 2 is the same as 1 over e to the 1/3. ln of that is just negative 1/3, and then you'll have negative 2/3, which is less than 1. So 1 plus negative 2/3 is positive. You have positive times positive. In other words, it's positive and it's increasing. Okay. So I'm just avoiding using my calculator because it's annoying. So anyways, I'll have a relative min right there. And you kind of have to figure out what the heck. Well, I don't even think they're asking for that. They're just asking for intervals of decrease and increase. So it's decreasing from 0 to this point and then increasing from that point on. Okay, hopefully that's right. I guess I could look at the answer. Yeah, so oh, it's increasing on, no, it's decreasing on the first. Okay, so we're good. All right, so that's number 21. We want number 49. So let me scroll down. My computer is not happy right now for whatever reasons. Okay, there it goes. Sorry, let me scroll back up here. What are we doing? Applying the first derivative test, apparently. Let me scroll down and find the thing. This is the one, I didn't bring my book home. Somebody caught me in my office right before I went home and I forgot my book. That was 3 weeks ago, and I haven't looked back. So I'm online looking at the book, and that's why it takes me a little longer. I have to toggle over and open up the book online. So I forgot my book in my office. Okay, so 49. Let me toggle over to, okay, so, oh, this is a exponential thing with a funny base. All right. Right, so the same beginning, the domain of this guy is all real numbers. You can put anything into an exponential and it won't sort of quote unquote break, right? So first I need to find the derivative, and again, it's a product rule. You got to be careful with these guys here. Taking the derivative, you always have to tack on an ln of the base, right? So, you know, if you're worried about finding derivatives of these things, you could think of it as y equals 3 to the negative x is the same as y equals e to the ln of 3 to the negative x, which is equal to e to the negative x ln 3. And then when you take its derivative, you just get this thing right back. So you get e to the negative x ln 3 times the derivative of the exponent, right? So the derivative of the exponent, in this case, negative ln 3. Okay? And then this thing right here is just 3 to the negative x. So it'll be 3 to the negative x times negative ln 3. Okay, so the derivative, first I'm going to leave x alone, and then the derivative of this part, yeah, I just found that here, so that would be times 3 to the negative x times negative ln 3, and then plus, now leave this x alone, so the derivative of x is 1, and then times this part of it, So it's 3 to the negative x. And then we're going to be cleaning it up and setting it equal to 0. We probably want to clean it up first, so because we're going to need to input values, right? So this will be negative. We could factor out a 3 to the negative x like that. And we end up with what? So the leftover bits, x ln 3 minus 1. Okay. We're going to need to set that equal to 0. Now we can set the parts equal to 0. This part here will never be 0. So you can kind of just toss that in the trash. But this part here we probably need to take a closer look at. So x ln 3 minus 1 is 0. So x ln 3 equals 1. So x is equal to 1 over ln 3. Okay, so our number line then, right here, 1 all over ln 3, whatever number that is. It's going to be positive, so in your test values you can just pick x is 0. Right, so you pick x is 0. When you plug 0 into here, you're going to have 0 times ln 3 minus 1, which is negative. This will be negative as well. It'll be negative 1. So negative times negative is positive. In other words, it's increasing. And then over here, you pick some obnoxious number. This is less than 1. Okay, so you literally just pick 1 if you wanted. But let's pick something that cancels out with the ln 3, right? So let's pick 2 all over ln 3. All right, so in that case, if I plug that into here, you have 2 over ln 3 times ln 3 is 2, and then 2 minus 1 is 1, that's positive, times something which is going to be negative, okay? So positive times negative is negative, so it's decreasing there. And then finally, by the first derivative test, that means we have a hill, and whatever's at the top of the hill is a max, so relative max. So there's a relative max. And you wanted to know the simplification in particular of this extrema. So you have a relative max at x equals 1 over ln 3. And then we want to plop that back into the function and figure out what it looks like, right? So 1 all over ln 3 equals 1 all over ln 3 times 3 to the negative 1 all over ln 3. Okay. As far as, some simplification, I don't see one. You could rewrite this as 1 all over ln 3 times 3 to the 1 all over ln 3. I mean, then I'd probably put it in my calculator and just be done with it. So it's not like there's those nice exponential cancellation laws here, because that ln 3 is not really touching the, well, all right, so we can probably rewrite this. Let's not just throw it in the trash, right? So it's 1 all over ln 3. I can rewrite this expression as, you can rewrite it. I don't think it's gonna, I just don't think you can do anything with it. It's just, it is what it is. And let's see what the book says while you're having trouble with this. The answer, yeah. Yeah, so I mean, that's kind of the answer they have there. The relative maximum is just this thing right here. How the heck do they write that? 1 over ln 3, and then, okay, so you're having an issue maybe with the E thing. So the book has 1 all over E ln 3. Probably you can rewrite this thing here. Maybe that's the issue. So sorry, I went off the page. This is the answer they kind of have in the book. So it probably has something to do with rewriting this in terms of base E. So if right here, this thing I have circled, let's extract it and kind of zoom in on it, right? So I'll have 3 to the 1 all over ln 3. You could rewrite it base E. as e to the ln of 3 to the 1 all over ln 3. Right? You can probably rewrite it so what is this thing then? That's e to the 1 all over ln 3 times ln 3, which is just the power rule, right? I brought the 1 over ln 3 in front. And then ln of 3 times 1 over ln of 3 is just 1. Okay, so you get e to the 1. And that's what you kind of see in that answer. So that's just e right here in their simplification. The commutative law of multiplication says you can put the e in front, and that's what their answer is. Okay, they also have this answer in the book too. So hopefully it's just a matter of doing your rules for exponents and using these inverse rules like this. Okay. Okay, so hopefully there's no mystery there. No mystery in math. It's kind of boring that way, but 51 is kind of nice. There's no craziness going on. It's 51. I got to find it. Oh, another weird log. So f of x equals x minus log base 4 of x, right? Okay. So same type of problem, I predict. You're going to need to get the derivative. So again, you're going to use a change of base formula for that thing, or you just kind of remember the rule for it. 1 minus ln x all over ln 4. So it's you think of it as a constant. So 1 over ln 4, and then you apply the constant rule for differentiation to that thing. Right? So f prime of x is going to be the derivative of x just 1 minus 1 over ln 4 times the derivative of ln of x, which is just 1 over x. So you end up with 1 all over ln 4 times 1 over x, which you can write as 1 over x ln 4. Right? Again, there's some issues with the domain. Like back here, I need to be conscious of the fact that the domain will be restricted from 0 to infinity. And right, I got to set this guy equal to 0. So it'll be 1 minus 1 over x ln 4. One critical number is where it's undefined, but it's not in our domain, so I don't have to worry about the 0. Let's just try to solve it. So put the 1 on the other side, 1 over x ln 4 here. Multiply both sides by x ln 4, or multiply both sides by x. And you get x is 1 all over ln 4. Okay. Right, so I come over here to my number line. I'm going from 0 to infinity. I'm going to mark 1 over ln 4. And I think your question again is on the simplification of the extrema. So just very quickly then, how do I get my, so I'm going to just presume this is an extreme value. I don't know if it's a max or a min. I'm going to cheat and get that answer. It looks like it's increasing here and then decreasing here. So I'll assume you could do the test value and stuff fine. Decreasing. So there's a minimum, and we're worried about how to simplify that answer. Okay. So min at x equals 1 over ln 4. And then you're going to plop that back into this formula back up here. So what do we get? F of 1 all over ln 4 is equal to 1 all over ln 4 minus this character right here. But I'm going to use this version of it, this form, right? So minus minus ln of 1 all over ln 4, right? All over ln 4. And then you could rewrite this insides part. So you have 1 all over ln 4 minus ln of ln 4 to the negative 1 all over ln 4. And then you do, then you do a power rule and bring that negative 1 in front. And what's going to happen is you're going to end up with 1 all over ln 4 plus ln of ln 4 all over ln 4. Okay, hopefully that's, let me look at the answer. Is that the dude? Oh, and then they found a common denominator, so they just added these together. So 1 plus ln of ln4 all over ln4. It's just all those little natural log rules and exponential rules you're sort of troubling with. Ain't real calculus, but just doing pre-calc stuff. Okay, so hopefully that's it. Okay, so next, let's look at what we got. 55. Where are you? Okay, so weird exponential. F of x is e to the -1 all over x minus 2. And we're doing the same old, right? Right, so first we need to get its derivative, and we're going to have to do a little bit of work there. Basically, it's going to be, let me make sure I'm on the screen. I have to toggle back and forth between the book and the webcam. So f prime of x is e to the -1 all over x minus 2 times the derivative of this thing. Okay, and let me rewrite that, right? So this would be e to the negative x minus 2 to the -1. And then you could do a power rule in here to get, so the derivative of this, you bring down the -1. -1 times -1 is +1. And then you have x minus 2 to the -2. So you subtract 1 away from the old exponent. Okay, so there are issues with this guy with regards to domain. In particular, we can't have x equaling 2. That's bad news. So in the domain, we need to note that it's going from -infinity to 2, and then union with 2 to infinity. Okay, so this guy will have e to the -1 over x minus 2 times 1 all over x minus 2 squared, right? And then we need to get the critical numbers. If you set it equal to 0, there would be a critical number where this thing is undefined, right? So whenever x is equal to 2, but 2 is not in the domain because originally we had this issue. It's a little technicality, but the critical numbers aren't officially at any place where the function's not defined. So certainly, yeah, there's critical numbers at x equals 2, but they're not really critical numbers because the thing doesn't even exist there. There's like an asymptote there, if you will. So you can try to solve it, right? You can divide both sides by this thing. E to the -1 over x minus 2, e to the -1 over x minus 2, and you just get 0 equals 1 over x minus 2 squared. And then you can multiply both sides by x minus 2 squared, and you get 0 equals 1, which means there's no solutions to that equation. Okay, so there's none of the traditional critical numbers where the derivative is equal to 0. Again, the only potential critical number could have been where this denominator equaled 0, okay, and the derivative. We can't have x minus 2 equaling 0, but that number is not in the domain, so therefore the thing isn't even defined there, so therefore it's not a critical number. The only other thing you worry about then is the, I guess, the interval of increase and decrease. So I'll put an open dot there at 2. And on either side, you still have to kind of check because the thing can jump over the type of increase or decrease as it goes through this point. Okay, so I'll do that and test value, sign, conclusion. But for the derivative, because this thing's squared, it's always going to be positive. So whatever number I put in here, it's going to end up being squared. Exponential, e to anything is going to be positive. This will be positive because it's squared. So it's a positive times a positive. It'll be increasing, and the conclusion is it's increasing, sorry. Over here, it'll be the same deal. You don't even have to do a test value. Okay? So you could say maybe there's some sort of, no, there's not a max. You wish there was a max here, but I think it'll be one of those cases where the actual you know, it won't have a max. For any number you give me, I can find a number that's greater than that if I put it into this function. It's going to go to infinity, in other words, in that direction. And then it'll probably go from negative infinity up here or something like that. So no critical numbers, no max, no min. Okay, but it's increasing everywhere. Okay, so that's 4.3. 4.4 junk. So let's look at 4.4. And we're looking at 27. Okay, so again, I got to kind of scroll over in the ebook. So just hang on. I would pause the video, but I don't really know how. I think it would break it, and then I'd have to end up uploading 2 videos. So if I stop the video, I haven't figured that out yet. Still kind of new to the whole. All right, so what are we looking at? Number 27. And finding points of inflection. Find points of inflection, discuss the concavity. All right, so 27. Where, oh, it's a secant. Ugh. All right. We'll see how this goes. Right, so we need the second derivative. So f prime of x is secant of x minus pi over 2 times tan of x minus pi over 2. And then times the derivative of the x minus pi over 2, which is just 1. So the chain rule says it's pretty much that's what it is. For the second derivative, I'm going to have to do a product rule, which I don't want to do, but oh well. So what do we got? Leave this guy alone. So I got secant of x minus pi over 2 times, take the derivative of this guy, which will be secant squared of x minus pi over 2 times the derivative of x minus pi over 2, which is just 1 minus 0, which is just 1. And then plus, now I'm going to take the derivative of this guy. So that will end up being secant of x minus pi over 2 times tan of x minus pi over 2. And then we still have this other factor, which I'm not taking the derivative of, right? So that ended up giving me a tan squared right there. You could factor out secant out of both of those guys. So f double prime of x. Yeah, they both have a secant. So secant of x minus pi over 2. And I'm hoping there's going to be some identities. Okay, so I'm always hopeful. We'll see. All right, so that we had all these Pythagorean identities, and one of those identities, what was it? So we had tan squared. Oh, it's not going to work, is it? Oh, how depressing. Yeah, that's not going to work because we're always, the sign isn't going to work out for us. What a bummer. Man alive, huh? Well, that's all right. We're just gonna have, that just means we got a little bit more work to do. I can always do this conversion though and turn it into kind of a quadratic. So you know, either rewrite the secant squared or rewrite the tan squared. I'm much more familiar with tan, so I'm going to rewrite the secant squared using the Pythagorean identity. So we get secant of x minus pi over 2 times, this will be tan squared plus 1. So you end up getting 2 tan squared of x minus pi over 2 plus 1. Okay. And yeah, I'm not seeing anything all that helpful. Yeah, tan cubed. Set it equal to 0, so you get the parts set equal to 0. Secant of x minus pi over 2 equals 0. And we're on the interval from 0 to 4 pi. So 0 to 4 pi. We're looking for where it's equal to 0, but also where it's undefined. right? Because those will be in, both potential inflection points. And then likewise for this character here, I want to do the same kind of thing. So I'll have 2 tan squared of x minus pi over 2 equals -1. Divide both sides by 2. You get tan squared times x minus pi over 2 is equal to -1 over 2. There's no way to get -1/2 out of this. So at least when it comes to the zeros, there's no zeros from this. It might be undefined at places though, so you kind of have to worry about that. So in particular, tan is sine over cosine. So I'm looking basically for where cosine of x minus pi over 2 is equal to 0. But if you think about it, I'm also going to be looking for those over here in this equation because secant is just 1 over cosine. So if I kind of, okay, so I need to worry about secant. If you think about what secant looks like, the thing will never equal 0, right? Because secant is kind of living off of the cosine function. So here's the cosine function, and then the secant guy would be like this on top of it. Okay, if you go x minus pi over 2, all that's going to do is move the secant function left or right. It's going to move it right. And that won't affect the fact that the secant will never equal 0. So this will really never happen. This guy is never going to happen. The only places that we have to worry about are these going to be these places here where the thing is undefined. So I really just have to solve this equation. In other words, I'm looking for where x minus pi over 2 is equal to something that causes cosine to be equal to 0, and the interval from 0 to 4 pi. And the places where that happens will be pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Okay. And then we can add the pi over 2 to the other side. So x will equal pi over 2 pi over 2 is 2 pi over 2, or pi. And then here, pi over 2 plus 3 pi over 2 is 4 pi over 2, which is 2 pi. And then here, 6 pi over 2 is 3 pi. And then 8 pi over 2 is 4 pi, but that's not in our interval. So these are the only potential inflection points. Right? And they won't be traditional inflection points because the original function's not defined there. Okay, so you're going to have undefined places, but you still have to check them when you go to your number line because your function can change concavity, okay, over undefined place. So what do we have? Pi, 2 pi, and then 3 pi, and then we want our test values, signs, and conclusions. Right. Okay, so let's do some test values. So I'm thinking stuff like pi over 2. And I'm dumping stuff into my second derivative, which is a big mess. I got it written as secant of x minus pi over 2 times 2 tan squared of x minus pi over 2 plus 1. Okay, this factor, because this is positive, the worst case scenario, it would be equal to 0, okay? And in that case, you would have plus 1. So what's going to happen is this whole thing is going to end up being positive no matter what. Okay, so the only factor you need to consider then would be the secant portion. So you're thinking secant of pi over 2, and you may want to remind yourself that secant is just 1 over cosine, right? Okay, so if I put in pi over 2, I'm really looking at this thing. 1 over cosine of pi over 2 minus pi over 2 is 1 over cosine of 0. 1 over cosine of 0 is 1. So it's positive, so it is concave up. Okay? And then we'll try x equals 3 pi over 2 and here. So putting that in here, 3 pi over 2 minus pi over 2 is 2 pi over 2, which is pi. That's -1. So sad face. Try x equals 5 pi over 2. So cosine of 5 minus 1 is 4 pi over 2. That's 2 pi, so that's positive, happy face. And then x equals 7 pi over 2 will probably be negative, sad face. So yeah, 6 pi over 2 is 3 pi, and cosine is negative there. So hopefully, let me look at the answer, see, make sure that's right. Yeah, concave down up on 0 to pi and 2 pi to 3. Yeah, we're good. Okay, so just a lot of annoying trig stuff. Right. Let's move on to the next guy. Next boy. Where are we? 4.4. That was 27. So 29. Oh, that was a scary one. All right. F of x equals 2 sine x plus sine of 2x on the interval from 0 to 2 pi. All right, so I need to go through and get the derivatives of this character. F prime of x. And you know, for setting it equal to 0, it may be in your best interest to go ahead and rewrite this guy as 2 sine x cosine x. So I would go 2 sine x plus 2 sine x cosine x. Hopefully I got that identity right. If not, it's going to be a real mess, but I'm 90% sure I'm right. I don't do that guy every day, but so f prime of x is going to be 2 cosine x plus 2, and then I need a product rule on this thing. So I would have sine x times negative sine x would be negative sine squared x, and then cosine x times cosine x plus cosine squared x. Okay. So f prime of x, I don't know how much help that's going to be. 2 cosine x minus 2 sine squared x plus 2 cosine squared x. And then f double prime of x, this is snowballing, right? 2 times negative sine x minus, I got to do a power rule and then a chain rule, so minus 4 sine x times cosine x, and then plus a power rule, chain rule, so 4 cosine x times negative sine x. Right? And then f double prime of x must equal negative 2 sine x, and then there's negative 4 of those, negative 4 of those, so that'd be negative 8 minus 8 sine x cosine x. And that doesn't work out too bad. So I set it equal to 0. There's no undefined places because this is just a composite of a bunch of trig functions. So I'll have you can factor out a sine, so negative 2 sine x, and then we get, what is it, 1 plus 4 cosine x. Right? That's sad because now we're not going to be able to kind of, so sine x equals 0 from this. In that interval, x will be 0, and then pi, and then 2 pi. And then this nasty thing, 1 plus 4 cosine x. And that makes me think I used the wrong identity. Oh, crap. I'll look up that identity. You know, I have to go on the web and make sure it's right. Sine 2x. What is the sine of 2x? Okay, any day now. That would be nice if you just... Sine 2x is 2 sine x cosine x. That's what I wrote. Let me make 1,000,000% sure before I get in too deep. I'm already in too deep, but where are you? sine of 2x is equal to 2 sine x cosine x. Yeah, I'm fine. So let's make sure this is right. I mean, really, so cosine of x is going to be negative 1/4. You know, the trouble with that is I can't use my brain to figure that out. X is equal to cosine inverse negative 1/4. You know, that's a bummer. Did I do something wrong? I mean, that's what I think. So this would have been 4, 4, you know, man. Sorry, I'm going to scroll over, see what the stupid book says. Of course, the book is not working. Let's see what the answer is. Yeah, it's a nasty answer, so that has to be right. Let's see what the book says. So they always give you like calculator solutions, and the range of cosine inverse is from 0 to pi. So it's going to give you the calculator answers in this range, and then you have to go and kind of get the ones in the interval you desire. So let's see what the calculator says about cosine inverse of negative 1/4. Home, my calculator needs to go home. So cosine inverse of negative 1/4. I need to make sure I am in the correct mode. So it needs to be in radians, and then I need to have approximate answers. So I'm getting 1.823, and that's a reference angle in the first quadrant. Okay, so wherever the heck, oh wait, pi over 2 is like 1, so this is over here actually. Let me convert that into degrees and see where it is. Oh, the thing's being a jerk. $104 degrees. So yeah, it's in this quadrant, and to get the answer in this quadrant, you have to take pi and subtract away this angle. So the reference angle that we need is going to be pi minus xc. So pi minus, second answer is, geez, so it's not happy about that. Pi is 180 degrees, man. Oh, I got it in the wrong mode. So I screwed up the mode, sorry. So let me get out of that mode and get back, oh great, back into mode, back in the radian mode. And I'm going pi minus this cosine thing. So that'd be 1.318 is the reference angle. So to get this other angle where cosine is negative, I need to figure this guy out, right? You probably could have just reflected, but this is the way we're kind of trained to do it, right? So in this case, it'll be pi plus the reference angle. So this is basically, this one is x1, and x2 is pi plus the reference angle, xr. So we go pi plus this 1.3-ish, so that looks like about 4.4597, so we have to round up, 4.460. So there's those two guys for our two extras, and then we go to our number line. and start graphing a lot of these guys. So I'm on the interval from 0 to 2 pi with the second derivative, and I have all these numbers, right? So 0, I need pi, and then I need 1.823, which is a little smaller than pi. I'm going to not draw it to scale. And then I need this other guy, which is bigger than pi, at 4.460. And then I'm using my second derivative, so I got to go through my test values, signs, and conclusions. So we're looking at x. So this thing, you know, you could go like pi over 6 or something like that. And here, where the heck is this thing? You know, you try like 11 pi over 12, something close to pi, and then x equals like 13 pi over 12, and then something close to 2 pi, so x equals 23 pi all over, what is it, 12. Okay. And then you're just plopping that junk into your calculator, and it looks like it's going to be in this first interval from 0 to 1.8, concave down, and then 1.8 the pi, concave up, and then pi the 4.46, concave down, and then 4.6 to whatever, to 2 pi, concave up again. And these are then points of inflection. Okay. Of course, the thing is, yeah, so those 3 points are your points of inflection. And hopefully that's it. I think the big problem is probably this reference angle thing that you're not used to doing all that much. Right? But it does come up in calc homework. I don't put stuff like that on tests, but I know it's in the homework. So reference angles, okay. All right, that's 29. 45. Let me scroll over. What are we doing? Second derivative test. 45 is f of x equals cosine x minus x on 0 to 4 pi. Okay, first derivative, sine x minus 1. And the point with the second derivative test, they want you to actually find the critical numbers here. Because if you tell the concavity over one of these critical numbers, it kind of tells you the max or min, tells you if it's a max or min. So I'm looking for where sine of x is equal to 1 on this interval. Right, so in particular then, that will be where x equals, and I think about my unit circle, where is sine equal to 1. So that's pi over 2, and then it's negative 1, and then 5 pi over 2, and then it goes to negative 1, and then, does it go too far, 7 pi over 2, and then back to negative 1 at 9 pi over 2. So that's okay, let me make sure. Pi over 2, 3, pi over 2, 2, 3, pi over 2, no. 4, 5, yes. 6, 7, no. Okay, so it's just those two guys right there. Okay, let me check again. Pi over 2, 3, pi over 2, 2, 3, pi over 2, no, because it's negative 1 there. And then 4, 5 pi over 2, yes. And then 6, 7 pi over 2, no, because it's negative 1. Okay, and then 7, 8, and we're out of the interval. Okay, right. Then I need to find the concavity. So you go to the second derivative, and that's just going to be cosine x, set that to equal to 0, and you could tell where the potential inflection points are. So that's just going to be at pi over 2, 3 pi over 2, 4, 5 pi over 2. It's all those. So pi over 2, 3 pi over 2, 4 pi over 2, oops, 5 pi over 2, 7 pi over 2. Okay, so the problem with the second derivative test is if the first derivative and second derivative are simultaneously 0, you can't use the second derivative test. Okay, so what you have to do is just go ahead and determine if they're maxes and mins using the first derivative. Okay, so in this case, we don't even require the second derivative if the only objective is to find the max and min. Okay. So the the second derivative, like I said, you don't use it. So why do we even bother with the second derivative test? It's mainly because it'll come up in Calc 3. You won't have this first derivative test to find maxes and mins anymore because the derivative changes because it's in 3 dimensions. You kind of have 2 slopes, one in the x direction, one in the y direction. So you'll see it there again, and you'll need it. Okay. Right, so I need to figure out, my test value, sign, conclusion. I'm plugging stuff into the first derivative, which is this guy here. So if you try pi over 4, sine of pi over 4, root 2 over 2, which is less than 1, so it's be negative. That means it's going down. And then if you try pi, sine of pi is 0, so that would be negative again. Really? That's not right. And it's going down. All right, so let me try this one again. Pi over 4. Sine of pi over 4 is 1 over root 2. That's less than 1. And then, right, that has to be right. And then let's try like 6 pi over 2. That's 3 pi. That's 0, so that's negative as well. My stupid computer is giving me a advertisement at the same time. Thank you, computer. Let me look at the answer. Yeah, it's always decreasing, so there's no extrema. Okay. But the point is, you can't use that other second derivative test because these are the same on the first and second derivative. Okay, 40 what? 57 now. All right. Ugh, an arcsecant, really? All right, the derivative of this guy, geez, I don't remember the formula off the top of my head. I think it's 1 all over, seems like there's an absolute value in there. It's just nuts. What is it, x squared minus 1 or something like that, and then minus 1, right? We need the critical numbers of this guy, and the critical numbers would be at x equals 0, and then plus and minus 1 from this, plus minus 1. So these are the places where this derivative is not defined. And then we could try to solve it and see if there's any solutions. So you set it equal to 0, put the 1 on the other side. Multiply both sides. Square both sides. Over here, when I squared this absolute value, I mean, literally it's x absolute value squared. But anything squared is going to be positive, so you no longer need the absolute value for this thing. Okay? Okay. You can distribute, so you get x to the 4th minus x squared, and then you can move this 1 over here. And then you hope to factor it, but obviously it's not going to factor. So you go to the quadratic formula and see if that's going to give you any help. let's make sure I got everything else right. So the quadratic formula says it's negative b, so negative negative 1 plus or minus the square root of b squared. So this thing, negative 1 squared, 1 minus 4 times a, which is 1, times c, which is negative 1, all over 2. So you get x equaling 1 plus or minus square root of 1 plus 4, which is 5, all over 2, which may look familiar to some of you. That's kind of like some weird golden ratio number or something like that. It seems like it is. I could be wrong. 1 plus or minus root 5. The minus portion is going to be negative, and you can't have negatives underneath square roots, so you throw that one out. So it's just 1 plus root 5 all over 2. So it seems like there's another kind of issue here with the domain of these things. So arcsecant is undefined all over the freaking place apparently, or not really. It's oh my gosh, it has a restricted domain, right? So if you think about the arcsine function, well, secant looks like this, right? And then you have to restrict the domain for secant from like 0 to pi. And then if you flip it about the y equals x axis, you get something else that's weird as well. But anyways, the domain is restricted from 0 to pi. Okay? And there's going to be an issue right in here at pi over 2. So you don't include that either. So the domain that we're worried about apparently is from 0 to pi over 2. And then unioned with pi over 2 to 0. So you need to take that in consideration when you start playing around with this thing. And I presume that this 1 minus root 5 over 2 square root of, well, I mean, that's bad news anyways, but okay, so I'm pretty sure this is the only guy that we have to worry about in this interval, and it may not even be in the interval. So this is pi over 2 to the pi, not 0. Okay, so I kind of have to get an approximation for that thing. So times square root of, well, let's just go 1 plus the square root of 5, and then divide that by 2, and then take the square root of that thing. And I'm getting 1.2-ish. Okay, so 1.27. Pi is, what the heck is pi, folks? It's 3.14. So it is in that interval. Which interval is it in? I don't know. But it seems like that should be our only real critical number. Okay, so what is pi over 2? Pi, it's like 1.5. So it should be over here somewhere. 1.27. Sorry. The other guy, yeah, it's not going to be good for the other guy. All right. For the second derivative, I hate to even think about it because of this thing. You know, it's going to be kind of a nasty looking. I guess we can take a look at it. So f double prime of x. I mean, there's two versions, right? There is the 1 all over negative x times the square root of x squared minus 1. And then there's 1 all over positive x times the square root of x squared minus 1. Because we have x values that are always positive, I don't think we need to worry about this derivative, right? So this is only if x is less than 0, and this is x greater than 0. So you kind of don't have to worry about that piece. And so, sorry, this is f prime of x. And so I need to take the derivative of this piece. So f double prime of x will be the derivative of this thing. And then to get the derivative of this thing, it's a matter of a lot of nastiness, right? This is the same thing as x times the square root of x squared minus 1 to the negative 1. So power rule, bring down the negative, and then I got x times the square root of x squared minus 1, now to the negative 2, and then times the derivative of the guts, right? So you need a product rule on that, so it's x, leave x alone times the derivative of this, which would be 1/2 times x squared minus 1 to the 1/2 minus 1 is negative 1/2, and then plus the derivative of all this mess, which is, well, the derivative of just the x. Whoops, I forgot the chain rule, right? So this would be times 2x at the end, and then plus leave this portion alone and take the derivative of that. So that'd be square root of x squared minus 1. Cleaning it up, what do we get? Negative, something nasty. Negative, this time, the 2 times the 1/2 will go x times x is x squared, and then all over the square root of x squared minus 1, and then plus this thing, square root of x squared minus 1, and then that's all over x times the square root of x squared minus 1 squared. We're getting the 0 and 1 are still, 0, 1, and negative 1 are still issues. Is 1 and negative 1 even in this interval? So negative 1's not, but 1 is, right? So we sort of have an issue at 1. So I didn't even include those when I was going through that. And then, so at 0, it's not defined, but at 1, there is something weird going on. Okay, anyways, with this guy up here now, I could take it and go x squared plus the square root of x squared plus minus 1 and set that equal to 0. This is squared and this is a square root. So they both have to be positive. And the only way for them to equal 0 would be if they both equal 0, right? And there's no way to have that happen, because if this is 0, this won't be 0. And if this is 0, this won't be 0, right? So that's not going to have any solutions, and you're just stuck with the same stupid points that you had before, right? Because we had this, sort of the same denominators. Well, no, it's not necessarily. Yeah, we still have the same issue. We had these are all critical numbers. So the only critical numbers I'm going to get from here are from the denominator, right? But the critical numbers that I'll get from there will just be the same numbers. So the potential inflection numbers from here will just be the critical numbers from the derivative. In other words, again, we can't use those as critical numbers, right? So, I mean, we can't use them in the second derivative test, sorry. So you're stuck with having to use the first derivative test in order to figure out maxes and mins. And it seems like these are the only points, and you need to put those into the first derivative to figure all this junk out. So you could do your test values, and I'll pick x equals something like 1/2. Okay, so if you're putting 1/2 in here, you get 1 all over 1/2 times the square root of, and that won't even work, right? Because you need this thing is not, it's not even differentiable when you go out of the interval from this interval isn't the domain, it's not working in the domain. Its derivative is kind of squished, right? Because you have to, it's, oh man, this is a brutal problem. So I'm sorry, when I said the arcsecant, its domain is from 0, but its range is, oh man, what a cluster. I hate to look stuff up because I don't have my stupid book with me. What the heck is the domain of this thing? I swear this was the domain, but it's not, is it? This is the domain of secant. The domain of arcsecant is like from negative infinity to 1, and then union to negative 1, and then union with 1 to infinity or something like that. So 1 and negative 1 and 0 won't even be matter of. So I need to look up the range, or sorry, the domain of arcsecant really quick. Well, I have plenty of knowledge about the domain of arc cosine. Thank you. I'm actually asking for the domain of arcsecant. You know. And the only place I know where to figure that out is my book, and my book is in my office. Domain, you wouldn't think that would be such a hard thing to look for. And believe it or not, half my screen has been demolished because there's a big black thing in my screen, so I can't see half my screen, making my life even worse. I'm trying to find the domain of arcsecant. Okay, I'm gonna have to do it the old-fashioned way. All right, so this is secant, right? And we have to restrict the domain to be here. The domain of this becomes the range of this. So the range of this has to be the domain of this, and this has to be the domain. This has to be it. So crap, I screwed that up. I'm sorry. I'm just doing it off the top of my head. This part is what's screwed up. I totally apologize. So our points like this. All right, so I'm going to need a new piece of paper. It's going from negative infinity to 1, negative 1, and then from 1 to infinity, right? And my points, my critical numbers from the derivative where this denominator equals 0, this is where it's undefined. These points are not in my interval, my domain, so I can throw those out. The only number I have to worry about are these numbers here, okay? And you know, there's 2 of them from this factoid, but I can't use one of them because, well, I could use them both, right? No, because I can't. Okay, so here I got to make sure the math is right, make sure I didn't make any silly mistakes. So I squared both sides. I got this thing is x squared minus 1. Okay, distribute, move this over, and so x squared equals this thing, but x squared can never be negative. Root 5 over 2 is bigger than 1 over 2. So if you subtract those, you're in trouble. That would be negative. X squared can't be negative, so you have to throw out that one solution. The only solution you should get is this 1.27 as a critical number. So 1.27 is in there. And then when we got the second derivative, doing all that work, where's the second derivative? Assuming I didn't make any silly errors, what I noted was we would get 3 potential inflection points from the denominator, right? So you get 0, plus, minus 1, but those aren't in the domain anyway, so you kick those out. And the only possible solutions you would get would be from this numerator. But I'm saying this numerator will never equal 0, so you won't get any inflection points. Okay? So it's always concave up or always concave down. And so you can just do one test value in each interval to get sort of at what's going on. So there aren't going to be any extrema over here. The only possible extrema are going to be over here. So from the second derivative on this interval, if you do a test value, x equals maybe like 5 or something like that, the numerator, this thing, all of this junk will be positive, but there's a negative out here. And then the bottom is positive, so it has to be negative. No matter what value you put in there, it has to be concave down, right? So it's concave down. And then what that means is if you have a critical number over a concave down, this has to be a maximum. Okay, that's what the second derivative test means. Oh my gosh, really? So let's see if I'm right. I'm going to go in and check my answer. Please be right. No. Answer. Computer is not responding. Answer, please, today. Oh yeah, well I got one of them. The other one, the other one for some reason, I threw that one out. That was in these solutions back here. The other one is from this other guy, which I threw out because I don't know. Because I said it was negative, you know. I don't know. Okay, so I screwed something up there, but I got one of them. 1 out of 2 ain't bad. Let's move on. Okay. Alrighty then. The last problems are easy. Let's see. All these limit problems are super duper easy. This is 4.5. Yeah. Okay. So let's look at these. 35, 39, 41. Where are you, 35? This one is a squeeze theorem. Okay, so note that sine of x or sine of 2x or sine of whatever x is in between -1 and 1. Okay. Supposing x is not 0, you can divide all of the sides of this inequality by x. And then if the limit of the two outer parts are the same, it forces this limit to be the same. Okay, so note the limit of -1 over x as x goes to infinity. This is just L over infinity form. Okay, so that would be 0. And then likewise, the limit as x goes to infinity of 1 over x is 0. The limit of this is 0, the limit of that is 0, so therefore the limit of this is 0 by the squeeze theorem. We saw the squeeze theorem, but we never saw it with regards to these limits that go to infinity. But it still works here. Sometimes you have to be careful, but this time you could pull it off. Okay. All right, next, 39. Okay. Again, well, for these, you can kind of, I mean, you got to be careful when you're playing around with limits, but in general, you can usually get away with just moving a limit inside of a function, so long as whatever limit you're getting when you do that is defined, right? If I moved it in and I had like this limit did not exist, then you'd be in trouble. But otherwise, you could pretty much bet that it's going to work out for the best. If you take the limit of this thing, you're plugging numbers, x going to infinity, like 10, 100, 1,000. You're plugging them in like here. This thing right here, if you were to kind of just zoom in on this piece of it, is the same as 1 over 10 to the x, right? And then you're plugging numbers like 10, 100, 1,000, a million into this, and it'd be 1 over something huge, 1 over infinity. Whenever you got 1 over infinity or L over infinity form, it's equal to 0. Okay? Anything over infinity is equal to 0, as long as this is some finite number. Okay, so this thing is just going to go to 0, and you have the log of the limit of 1 plus 0, which will be 1, and the log of 1 is always equal to 0. Okay, okay, next. 41. Okay, so we got one of our arctan friends. Limit as t goes to infinity of 8t to the negative 1 minus arctan of t. Right, so this guy will go to 0 for the same fact that this last guy went to 0, right? It's really 8 over t, and if you put in t equals 10, t equals 100, t equals 1,000, it's just going to zip off to 0. So this guy here is the troublemaker. And what is that thing? Well, arctan is just tan flipped on its side, right? And there's horizontal asymptotes at pi over 2 and negative pi over 2. So as arctan goes to infinity, so as t goes to infinity, arctan is getting really, really close to this asymptote pi over 2. Okay? If I was going the other direction, it would go to negative pi over 2. So this thing is going to pi over 2, and there's a negative in front of it, so it should equal negative pi over 2. Okay. Oh, that's it? Okay. Sorry about butchering that one. Oh my gosh. My brain wants me to go back and redo it, but I no, I'm telling it no, and hopefully that's good enough, what I did there. I'm not going to put it on a test though, so don't worry about it. All right. Hopefully that's good enough. If it's not, let me know, and I'll do another video for that problem. I may do it just out of some weird sense of obsessive compulsion, but hopefully that's good enough. Okay, well, bye.